All right, welcome to Chemical Thermodynamics. I have not used this technology with PowerPoint, so try to bear with me if I have some mess ups. So this chapter is pretty much about whether a reaction will happen or not. That is the whole point of this chapter. Yes, it will happen, or no, it won't happen. Okay, so let's see. All right, so thermodynamics is the study of energy and its transformation. So far, we've talked about thermochemistry and we've talked about enthalpy and heat, but I did briefly mention to you earlier in the year that heat or enthalpy is not the only thing that determines whether a reaction will happen. We have to talk about entropy, so that's going to be a new word we talk about in this chapter. Remember that the first law of thermodynamics says energy is conserved, meaning it's neither created nor destroyed. It gets transferred, rearranged, but it doesn't just appear or disappear. Okay? The College Board has steered towards using thermodynamically favored processes instead of using the word spontaneous. So that's going to be abbreviated TFP. Really, they mean the same thing. But they are trying to use thermodynamically favorable instead of the word spontaneous anymore. Okay, so these are reactions that will occur on their own. All right, meaning they happen. You don't need to have extra energy involved. They will go without any help, extra help. Okay, if a reaction will go on its own, you can't go backwards on its own. So if it's thermodynamically favorable one way, it is not thermodynamically favorable to go the opposite direction in a chemical reaction. So for example, rusting of iron. You set a nail outside, it rusts. That's thermodynamically favorable. It will happen no matter what you do. If you set it outside, it will rust. It might take a while, but it will rust without any extra help or input of energy. Okay? Gasoline burning in your car is thermodynamically favorable. It happens on its own. You take salt, you dump it in water, it will dissolve. That's a thermodynamically favorable process. It happens on its own. You dump the salt in the water, boom, it dissolves. Okay? Anything that's, like I said, thermodynamically favorable one way, it's irreversible, meaning you can't go backwards, at least without any work. Okay? Remember that a reaction happening does not determine how fast the reaction happens. You can have a thermodynamically favorable process, but it could take forever for the reaction to actually occur. So like rusting is not a very instantaneous reaction. It's favorable. It will happen, but it does happen kind of slowly. The kinetics of a reaction don't determine whether a reaction will happen or not. Okay? All right, so look at. We've got water. Water liquid to water solid at negative 10 degrees. If you take liquid water and you store it at negative 10 degrees, it will turn into ice, also known as solid water. That's thermodynamically favorable. Okay? However, if you take ice, solid water, that's this guy right here, and you try to get it to turn to liquid at negative 10 degrees Celsius, that is not going to happen. Water does not want to be a liquid at this given temperature. So that is not a thermodynamically favorable process under these conditions. Okay? All right. In general, nature tends to favor exothermic reactions. Okay? So negative delta H. All right, so you can read all of this. That doesn't mean endothermic reactions won't happen. They absolutely can happen, but nature tends to prefer towards a decrease in energy being released. Okay? But for example, endothermic reactions, evaporation is endothermic. To take water and to evaporate it, to turn into a gas, energy goes into the system. That happens, and it's thermodynamically favorable, and it's endothermic process that is favored. Dissolving. So most dissolution processes are endothermic, meaning like if you take a bunch of salt and you dissolve it in water, it actually cools down a little bit. We did this with sodium acetate also. You take some sodium acetate and you dissolve it in water and it gets pretty cool. That's endothermic. Now that reaction happens spontaneously and or is thermodynamically favorable, and it's endothermic. So you can't say that endothermic reactions will never happen. They absolutely do happen. However, exothermic reactions are favored. Okay? exothermic reactions can also not occur. Just because something is exothermic doesn't make it 100% that it will occur, so it won't always proceed. So look at this example of ammonia and oxygen making nitrogen monoxide and water. The delta H is negative 909. This is how much energy it's released when this reaction happens. This reaction, though, doesn't produce very many products. The reason that is it's said to be what's called under kinetic control. This reaction has such a high activation energy, and your reactants are generally stable, that even though it is exothermic, it tends to not occur, at least not without any extra help. Okay, so again, an endothermic process. Potassium chloride dissolving in water is endothermic. This is how much energy goes in. It cools down. If you take potassium chloride and you put it in water, it will dissolve. That is a thermodynamically favorable endothermic process. Okay? All right, entropy is disorder or randomness. So signs are a big part of this chapter. So delta S. The delta means final minus initial, so it's products minus reactants. The more negative delta S is, the less random or more ordered something is becoming. The more positive delta S is, favors more disorder or more randomness. Okay? And in nature, reactions tend to favor being more disordered, so a more positive delta S. Things tend to become disordered a lot easier than they can be ordered. Okay? So look at the potassium chloride example. When potassium chloride, though it's an endothermic process, it breaks apart into ions. Ions are more disordered than a solid crystal lattice. So the disorder is what helps the potassium chloride dissolution process to be favorable. You have an increase in entropy. Okay? So a few things that affect randomness or disorder or entropy, all of those mean the same thing, are the states of matter. Okay, so this is the easiest. Gases are the most random, they have the most disorder, then liquids and solids have the least amount of entropy. All right, the next one is the number of particles. So when compounds break apart into more parts, it is considered to have more disorder or more entropy, more randomness. Volume is going to be usually for the size of the container. So the greater the size of the container usually increases entropy, especially because gases now have more room to move around, meaning they can become more random. Temperature increases entropy because if you increase temperature, molecules move faster, and if they move faster, they have the ability to become more random. Okay? So your first law of thermodynamics is the fact that energy is conserved. We've talked about that multiple times. The second law of thermodynamics talks about entropy, which is randomness, and it's the fact that in the universe and everything around us, things tend to become disordered more randomly on their own. Entropy is constantly increasing. The third law of thermodynamics is really interesting, and it talks about the idea of delta S, entropy, being 0. Remember that as the temperature approaches absolute 0, molecules cease to move, and so entropy equals 0 is saying that this idea that there's absolutely no disorder anywhere in any sort of crystal or solid as the temperature approaches 0. So this is the third law of thermodynamics. So let's talk about delta S being greater than 0, aka what they're saying is delta S is positive. Increasing entropy is what delta S positive is. So melting, solid to liquid. Liquids move more freely, so melting is an increase in entropy. Vaporization, that's liquid to gas. Gases move more freely than liquids, so vaporizing is an increase in entropy, positive delta S. Reactions where products are the same phase as reactants but contain more particles. So breaking apart into more particles is an increase in entropy or a positive S. Most solution making is an increase in entropy, usually because you're taking a solute, which is a solid, and a solvent, which is usually, let's say, water, and you're taking the solute and dissolving it, and the solid is now breaking apart into ions. Ions move more freely excuse me, than solids. Adding heat increases in entropy because molecules can move more freely. Increasing the volume of a gas, more space, more freedom to move, more disorder. Okay, so let's give an example. So this is nitroglycerin. It's a liquid. Okay, this is a huge chemical reaction. Look at all these products. Look at all these gases that are formed from the decomposition of nitroglycerin. So look at a tiny amount of this guy right here releases this much pressure, 270,000 atmospheres of pressure in a tiny amount of time because you're producing so many gas particles. So again, this is a huge entropy increase. You're going from 4 liquid molecules to 6 plus 12 plus 10 plus 1 gas molecules. That's a huge increase in entropy. Okay, so let's look at melting. Solid, organized water, held together with hydrogen bonding. You weaken the intermolecular forces, now it's less organized. You've got liquid water, aka more randomness or an increase in entropy. Okay, liquid to gas, also known as vaporizing, you completely break intermolecular forces and completely increase entropy, more randomness. Okay, look at a salt. Here's an ionic compound, some sort of salt, organized very well. And then you dissolve it in water, and now the salt breaks apart into particles. There's more randomness or more freedom to move here. So this is an increase in entropy. Okay, now delta S less than 0 is implying that delta S is negative, which is a decrease in entropy. So trying to take a gas, let's say this is oxygen, and dissolve it in liquid water. Well, the oxygen by itself is moving around pretty freely, but if you force it to dissolve in water, you have a decrease in entropy because now the gas doesn't have as much freedom to move. So it's more ordered, also known as less disordered. So that's a decrease in entropy. Okay, this is your heating curve. Again, as you move up the heating curve, entropy increases. Solid is the least amount of entropy, and then liquid, and then gases have the most entropy or randomness. So obviously going backwards would be a decrease in entropy. Okay. These are Boltzmann distribution curves, right? More particles at higher temperatures have more kinetic energy. If they have more energy, they move faster. If they move faster, they are more disordered, aka greater entropy. So let's practice. We have all of these guys. How many are there? Let's see. Oop. Okay. So predict whether delta S is positive or negative. So delta S is entropy, and it's positive if it's more disordered or more entropy, and negative if it's less. So liquid to gas should be positive delta S. You're becoming more disordered. Ions combining to form a precipitate should be negative. That is less disorder. Ions move more freely than a solid, so negative delta S. So now we have a solid and a gas going to just a solid. So the gas moved around freely, and now there's no gas anymore. So this is a negative S. That's a decrease in randomness. Okay. This is delta G. This is 2 gas molecules going to 2 gas molecules. So no change in delta S. Okay. This is a solid and a liquid going to just a solid. So this is a negative delta S, less disorder. This liquid had a little bit of disorder in it, and now it's gone. This is a solid going to a solid and a gas. So we should be increasing entropy because we've produced a gas that can now move around more randomly, positive S. All right, so which of these has greater entropy? A metal at 273 Kelvin or the same metal at 400 Kelvin? The hotter a metal is, or any substance is, the more freely it can move because it has more kinetic energy. So the metal at 400 should have greater entropy. Okay, a flexible soft metal like lead, or a diamond, which is a covalent network rigid solid. The flexible soft metal like lead, I know that sounds kind of contradictory because lead doesn't seem soft, but relative to diamond, it is. The lead will have more entropy, more freedom to move. Remember, metals are malleable because they have those sea of electrons. So the metal or the lead should have greater entropy. Two samples of the same gas, same temperature, and one has a pressure of 1 atmosphere and the other has a pressure of 0.5 atmospheres. They're indirectly talking to you about volume in this problem. So the one under 1 atmosphere is probably smaller space, and the 1.5 of an atmosphere is probably not, is probably in a bigger container. Bigger container under less pressure will have greater entropy, more freedom to move if they're under less pressure, aka potentially a larger volume. Okay, all right, so this is where I'm not used to going back and forth. Calculating delta S is very easy, okay? Just like delta H, if you're given values for S, it's products minus reactants. Remember, final minus initial. And then, of course, you have to pay attention to the coefficients, okay? The units for delta S are joules per mole Kelvin. They will either be, the S units will be given, or you can look them up if you're doing problems in your book, okay? So, look at this reaction. N2 plus O2 makes N2O4. So you need to balance it. Got to put a 2 in front of the O2. See, if I try to use my pen on here, it never goes well. Let's try. Let's see if I can write on here without it messing up. Whoa. Do you see my cursor? I don't even see it. Okay, let's try this. See if I can do it with my, okay, that's good enough. So there's your 2 for the balance. And then I gave you the numbers of all of the substances. So this is really just plug and chug. Products minus my 2 reactants with their coefficients. So you do products, so let's see. It's not letting me. So I'm trying to use my tablet because I can't write with my cursor very well, and it's not letting me. Let me try plugging it up. Okay, let's just 3, 0, whoa, 4. This is really hard to do. 0.2. So products minus reactants. So my N2 is 191.5 plus, don't forget the 2 times the oxygen is 205. So products minus reactants. When you calculate that out, you get negative 297.3. Okay, so a negative delta S, that means entropy is decreasing. So it's becoming less, think of the minus as less random, also known as more ordered. So look at it. You're taking 1 plus 2, 3 gas molecules, and you're forming only 1 gas molecule. So you had 3 molecules of gas moving around and now you only have 1. That is less disorder, less randomness, a negative delta S. So yes, the sign makes sense. Okay, I'm not going to do this one with you. Ooh. I have nitrogen and oxygen making nitrogen dioxide. Okay, if you look up in your book the values, you have products, so 2 times the nitrogen dioxide, minus reactants, so the nitrogen gas must have been 192 plus 2 times the oxygen gas, and you get negative 122 joules per mole. I guess there should be a Kelvin right there. Sorry about that. So delta S is negative, meaning less disorder. You're going from 1, 2, 3 molecules of gas to only 2 molecules of gas. That's less random. 3 molecules of gas is more random than 2 molecules of gas. So the sign should make sense. Okay? All right, so the point of this chapter is tying all of these concepts together, the enthalpy and the entropy, and then temperature, and determining will the reaction happen. So delta G stands for Gibbs free energy, and they call it free energy because it's the energy that has freedom to do work for you if it's produced from a reaction. So let's say you get energy from a reaction. You get your Gibbs free energy. You can do that. You can take that energy and use it to do work for you, like turn on a light bulb. Okay, so this is the end-all be-all, will a reaction happen? Okay, remember these little circles mean standard conditions, which are 25 Celsius or 298 Kelvin and 1 atmosphere. So if delta G is positive, the reaction is not going to happen, at least not without help. So reactants are favored, meaning the reactants just sit there and don't turn into products because the reaction is not going to happen. Okay. If delta G is negative, that means the free energy is being released and it can be used to do work. It's a thermodynamically favorable process. So just like up here, if delta G is positive, you can think of it as in you would have to add energy, so not just heat anymore, add energy, G, if you want the reaction to happen. It's not going to happen on its own. Okay, so if delta G is negative, the reaction favors the products, meaning you're making products. If you're making products, a reaction is occurring. Okay, if delta G comes out to be 0, the reaction is said to be at equilibrium, meaning both the reactants and the products are favored equally because they're going back and forth and back and forth. Okay, for this equation up here, the delta H equals delta T enthalpy minus T delta S. Temperature needs to be in Kelvin. Okay. Also, you'll notice that the entropy units, the S units, and the H units are different. H is almost always in kilojoules per mole, and S is almost always in joules per mole. So you're going to have to make them both the same. I will tell you delta G tends to be given in kilojoules per mole. So I will be converting most of my numbers to kilojoules for these problems. Okay, so let's talk about signs. So exothermic is a negative delta H, endothermic is a positive delta H. Increasing entropy or more randomness is positive S. Decreasing entropy is negative S, less randomness, more order. And then the end-all be-all. Reactions tend to release energy, be exothermic, and they tend to increase in entropy, which is more disorder. Okay? All right, so these thought problems. Here's how I do them. These are all conceptual. You see them very often conceptually. I'm going to switch over to my tablet because I'll do this scenario on the tablet. It looks like we have a exothermic delta H and an increase in entropy. And we want to know what conditions, if any, will the reaction happen. So let me click over. All right, let's see. Is this going to work? Give me a second. This was so much easier in the acid-base unit, huh? Let me pause while I figure this out.